Hello and welcome back. This lecture is continuation of higher order ODE. So in the last lecture we were discussing about linear independence, linear dependence, how we can check linear independence and linear dependence using the Wronskian. If Wronskian is non-zero, it means the set of functions is linearly independent. If the Wronskian is 0, it means the set of function is linearly dependent. Okay, so let's move forward. So if we have an order n ODE, it means it can have n linearly independent solutions. Okay, so if y1, y2 up to yn are n linearly independent solution, to the homogeneous equation of order n, then general solution is given by the linear combination of these solution c1y1 plus c2y2 up to so on cn yn. It means any other solution can be written in the form of this solution. For like some particular values of ci's, that solution can be written in this form. Okay, so now this was about homogeneous equation. If you have non-homogeneous equation, the general solution of non-homogeneous equation is given by y equal to yc plus yp, where this yc is called complementary solution and yp is called particular solution. This complementary solution is the general solution to associated homogeneous equation. See, everything is just very similarly extended from second order. That's why we discussed second order before. And particular solution can be any particular solution to the differential equation. This complementary solution always have n constants like c1, c2 up to so on cn. So this yc will contain n constants. This yp won't have any constant. This is a particular solution with no constant involved. Okay, so in general this whole solution is going to involve n constants. Okay, so this was the discussion how we write our general solution when we have yc and yp both. Now we move forward to homogeneous equations with constant coefficients. and the general form is an, the nth derivative, plus an minus 1, the n minus 1th derivative, up to so on, a1 first derivative plus a naught equal to 0. This is the homogeneous equation with constant coefficient, where we are saying these ai's are constant. The coefficients are constant for I between 1 to n. Okay. After this, we are now taking reference with the second order. After this, we learned how to write the characteristic equation, right? So the characteristic equation is going to be an r power n. For the nth derivative, we are replacing by r power n, plus an minus 1 r power n minus 1, plus up to and so on, a1r plus a naught equal to 0. So this is the characteristic equation of above homogeneous equation with constant coefficients. Okay. And if you remember, if you find a root of this characteristic equation, so suppose r is the root of this characteristic equation, then e power rx is going to be the solution of homogeneous equation. So we discussed three cases: if roots are real and distinct, if roots are equal, if roots are complex. So same here, we are going to have three cases. So we have the characteristic equation, then we calculate the roots of this equation, and then we talk about the three cases: if the roots are real and distinct. So now we have like n roots. Previously we had just two roots, so it might be possible two roots are real and distinct, two roots are say repeated, other roots are complex. Anything is possible, right? So in a single problem, we can have all of these type of root: real, repeated, and here say we have complex. Complex actually needs more space, but that's okay, let's write it down. So suppose you have k roots which are not equal. So corresponding to those k roots, we are going to write our complementary solution. So corresponding to these k roots, we have c1 e power r1x plus c2 e power r2x ck e power rkx. Corresponding to these k roots, this is going to be a complementary solution. Similarly, suppose you have r1, r2, if rk repeated roots, then what you are going to do is, it's c1 plus c2x up to and so on, ck x power k minus 1 e power rx multiplied with it. This is the corresponding part of the complementary function. If you have complex root, okay, so if the roots are not repeated, it's same as the case in order 2, then you will write the general solution is e power alpha x c1 cosine beta x plus c2 sine beta x, like this. Okay, but it might happen that you have complex repeated roots. What will you do then? Okay, let me write down that also. And in the next lecture we are going to see examples. We will see one example in this lecture also. So if we have complex repeated roots, then what we will do? Let's see. So suppose you have alpha plus I beta, this root, and this root is repeated k times. So basically you are talking about 2k roots, right? Because you have alpha plus beta, alpha minus beta, and you are repeating them k times. So you are repeating 2 roots k times. So total 2k roots you are talking about. Okay, let's see. Complex roots always occur in pair. Okay, so the corresponding part in complementary solution will look like e power alpha x c1 cosine beta x plus d1 sine beta x, corresponding to the first root, plus x times e power alpha x c2 cosine beta x plus d2 sine beta x, and so on till x power k minus 1 c1 ck cosine beta x plus ck sine dk sine beta x, like this. Okay, so it's very similar to the real repeated roots. First root we are keeping it as it is, second one we are multiplying by x, the third one we are multiplying by x square, and the kth one we are multiplying by x power k minus 1. Okay, so let's see one example and then it will be more and more clear to you. So our example is here. The roots of a characteristic equation are given by, so these are the roots of the characteristic equation. I'm directly writing the roots, so you don't need to find out the roots in this example. 2, -3, -3, 1, 1, 1, 1 plus minus 2i, 1 plus minus 2i. Write the general solution to this homogeneous differential equation. Okay, so basically in this case we involved all the possibilities. There is one real root which is not matching to anything. There is real repeated root -3 and -3. There is a repeated root 1 real repeated root, and there is complex repeated root. So with the help of this example, you will be able to understand the whole process. So let's write down the solution. Okay, so our yx is going to be corresponding to 2. Since 2 is not matching to anyone, we have c1 e power 2x. Corresponding to -3, we have c2 plus c3x e power 3x. So if a root is if we have n roots, we are going to involve n constants. So you can remember it that way also. If we have -3 2 times, so we are going to involve 2 constants, c2 and c3. Now 1 is repeating 3 times. So 1 is repeating 3 times, right? So we have c4 plus c5x plus c6 x square times e power x. I want to write this in the same line. E power x corresponding to 1. Now we want to write down corresponding to 1 plus 2i. So e power x c7 cosine 2x plus c8 sine 2x corresponding to 1 plus minus 2i, but we have one more 1 plus 2 minus 2i, so we multiply that one with the x. c9 cosine 2x plus c10 sine 2x. So here we have total 10 constants, so we can say the total number of roots should be 10. Let's just count. 1 2 3 4 5 6 7 8 9 10. We have 10 constants and 10 roots. So this is how you write down your general solution if you have the roots. Okay, bye bye. Practice some more problems, and in the next video we are going to take some differential equation and we'll see how to solve them. Bye bye.